In this video, I want to talk about metastability and how we can use synchronizers to reduce the probability of having metastable circuits. So, in the previous video, what we saw was that we had two registers that were connected to each other back to back with a combinational logic circuit in between, and both of these registers were getting exactly the same clock signal. So in that specific circuit, we didn't have any asynchronous input. But usually when we have asynchronous inputs, that usually happens when we have user interface, these asynchronous inputs might violate the dynamic discipline. So let's just take a look at one example here. Let's just assume we have this D flip-flop. We have this button which is connected to the ground using this resistor. And this side, if you remember from before, this is VDD or 5 volts. And this one is GND or 0 volts. So what we want to do is that we want to record the state of this button. So when the button is open, the input D is connected to the ground using this resistor, so its voltage is going to be 0. When the button is closed, D is going to be connected to VDD, so the value for D is going to be 1. So we want to basically record what is the value of button at any given time. So in this flip-flop, what happens is that at the rising edge of the clock, we take a sample of D. If the button was open, that means that D is 0. If the button was closed, that means D is 1 now. So 3 different cases that can happen. The first case is that the button is closed way before the aperture time of the flip-flop. So this is case 1, when D became stable even before the T setup time. So in this case, on the rising edge of the clock, we get a sample of value D, and then after a short amount of delay, which is as a result of the internal delays of the flip-flop, the change will be reflected in the output of the flip-flop. The second case is that the button was open, so that means D was 0, and then it became 1 after the hold time. So that means that this change of button was not recorded, right? So D was 0. At the rising edge of the clock, we got a sample of D which was 0, and then after some delay, which is again dictated by the internal components of the flip-flop, we have that 0 being reflected in the output of the flip-flop. So these were the 2 cases that we didn't have any problem. But what if while we are in aperture time, the value for D changes? Or in another word, what if during this time we press the button? So what would be the output? So that is something that we don't know, because for the real life flip-flops, the inputs need to be at least T setup time before the clock edge, and at least T hold time after the clock edge. So during this period, the D needs to be stable. Otherwise, we don't know what is going to be recorded. So that is what is usually called causing a metastable state for our flip-flop. So for bistable devices, we usually have 2 stable states and a metastable state between them. For the flip-flops, which is an example of a bistable device. We have two stable states. Either the output is 1 or 0 and one metastable state. So if flip-flop lands in a metastable state, it can stay in that state for an undetermined amount of time. So that is the general definition of metastability. We have two stable states and we have this metastable state in between them. As you can see, if you have a ball in this stable state, the ball doesn't move. But if you have a ball in this mountain, in this peak, so it is possible that the ball falls into the left stable state or the right stable state. So this is something that happens, but we don't know when that happens. So in flip-flops, since we have cross-coupled gates that are connected in this way, in this configuration, after some time, this metastable state will be either going to 0 or 1. Again, we don't know which way, but we know that it doesn't stay in this state indefinitely. But how can we model such a thing? So without going into very much detail, if a flip-flop input changes at random time, the probability that the output Q is metastable after waiting some time is determined by this equation. Again, I'm not going to go into more details of how this equation is being derived. So we have P of TRES or the resolve time greater than T. This P is the probability function. So the probability of the resolve time being larger than T equals T0 over Tc. You know Tc from before. Tc is the period of the clock, multiplied by E to the negative T over tau. So you know this is an exponential function. Since the sign of the power is negative, that is a decreasing exponential function. So it has a form like this. So this function, P of T-res greater than T, has a value of T0 over Tc when T equals 0. So this is T equals 0. And after that, it exponentially decreases to 0. So as you can see, the larger this T resolve time, the smaller the probability. So the larger the T resolve time, the smaller the probability that the flip-flop stays in the metastable state. So intuitively speaking, T0 over Tc is the probability that the input changes at a bad time, basically during the aperture time. And we have tau, which is the time constant for the flip-flop. And that is another parameter that we don't have any control over, at least in terms of the analysis that we do. If you are building the flip-flop from the ground up, then we have some control over how this value for tau is related to the design of the flip-flop. But for us, we just assume it as a time constant for the flip-flop. So I said all of these things to get to this conclusion, that if we have a flip-flop that has an input that happens at a bad time during the aperture time, and that results in a metastable state, if you wait long enough, the output will be resolved either to 0 or 1. So not necessarily what you wanted, but it doesn't stay in the metastable state for long. So now that we know generally what is a metastable state, let's just talk about synchronizer. So for the circuits that get inputs from users, or if you have some systems that use different clocks and they are forced to interact with each other, it is inevitable to have asynchronous inputs. So while synchronizers try to reduce the probability of metastability, they cannot make it completely zero. So the final goal of a synchronizer is to make the probability of failure or the metastable state lower. So this is the symbol that we use for synchronizers in digital logic circuits. We have the data input that goes to a box. We have the Q, and then we have the clock signal. But you might ask how this synchronizer is being built. So the answer to this question is kind of straightforward. If you remember what we did when we wanted to go from a D latch to a D flip-flop. If you remember, we said that for D latches, the output of the latch is dependent on the time that clock is 1. To make the D latch be only sensitive to the clock edge, we used two D latches back to back. So one of them was acting as a buffer. So a similar concept is being applied to create a synchronizer too. So if you put two flip-flops back to back, one basically, the first one acts as a buffer for the second one. So let's just take a look at this design. We have the data input here. So this is the asynchronous data that we want to avoid. This data goes to the first flip-flop. The output of the first flip-flop is being fed to the input of the second flip-flop, and that creates the output Q of the synchronizer. So we have this internal signal that might be in a metastable state as a result of having an asynchronous data input. So if we have our clock signal to be like this, and if I label these two, or if I highlight these two rising edges of the clock, we know that Tc, or the period of the clock, is basically the time between the two rising edges, between the two consecutive rising edges of the clock. So assuming that we have a data that happens at a bad time, what happens is that D2 will go into a metastable state. So this metastable state would usually resolve in T-res. But for us to be able to capture the true data in the second flip-flop, we need that the input of the second flip-flop be a stable at least T setup time before the next rising edge of the clock. So internal signal D2 has Tc minus T setup time to resolve to either 1 or 0. So we have Tc to be equal to T-res plus T setup. or more accurately, Tc is greater than or equal to Tres plus T setup, which means that Tres is less than or equal to Tc minus T setup. But this is the constraint that we have for the resolve time. So now, based on this, basically the maximum value for the resolve time, we can rewrite the previous equation that we had for the probability of failure or probability of metastability. So if we just simply replace the T resolve that we had before with Tc minus T setup, that is the probability of failure at the end of Tres. So again, this is a probability. So depending on the value for the time that passes, this probability would go down. So if you wait, let's say, 1 second for a circuit that works with a 5 megahertz clock signal, after 1 second it is definitely resolved, right? Because you have waited very long time. But when Tc is in the order of several nanoseconds, then the maximum amount of resolve time is going to be in the order of nanoseconds too. So it is important for us to know what is the probability of failure, right? Because when you are working with real numbers, that probability is not going to be exactly zero. It can be very small if you design your circuits correctly, but it is not necessarily zero. And when you have these failures to happen several times over seconds or thousands of times over hours, for example, then you see that even these very small probabilities would add up. So if asynchronous input changes once per second, the probability of failure per second is P of failure. So the equation that we had in the previous slide. However, if input changes n times per second, which is usually the case for logic circuits, because we usually work with high frequency clocks and we have so many inputs that are changing all the time. So if we have input changes n times per second, the probability of failure per second is going to be n times the probability of failure. So you can think of it another way too. If the probability of failure per second is n times the probability of failure, if you reverse this definition, you can say a synchronizer fails on average 1 over the probability of failure per second. So this is what is usually called as the mean time between failures. So 1 over the probability of failure per second is the mean time between failures. So let's just take a look at one example, so everything that I discussed make more sense. So let's just assume we have this synchronizer. Again, we have the asynchronous data input that goes through the first flip-flop. The output of the first flip-flop is being used as the input of the second flip-flop, and then we have Q that will be used later on. And we hope that the probability of failure or the probability of metastability using this synchronizer will be lower than the time that we didn't use any synchronizer. So for this circuit, we suppose that TC, or the period of the clock, is 1 over 500 megahertz. So that means that our clock signal is working with 500 megahertz per second. And remember, mega was 10 to the power 6. So 500 million times per second, our clock signal changes from 0 to 1 and 1 to 0. So that makes the period of the clock to be 2 nanoseconds. For our circuit, the value for tau is going to be 200 picoseconds, and that's a given value. We don't have any control over it. Then for T0, we have 150 picoseconds. For T setup for the flip-flops, we have 100 picoseconds. And finally, we are recording 10 events per second. So now, based on these inputs, let's just see what is the probability of failure and what is the mean time between failures. So the answer to this question is very simple. We just plug in all the numbers that we have in the equations. So for T0, we had 150 picoseconds. For TC, we had 2 nanoseconds. And then we had e to the negative TC minus T setup over 200 picoseconds. So if I calculate this, what I get as the probability of failure for each event is going to be 5.6 multiplied by 10 to the power negative 6. So as you can see, this value is very, very small. So it's in the order of several 1 millionth. But don't make the mistake, even though this is very small, but since you have 10 events per second, the probability of failure per second is going to be 5.6 multiplied by 10 to the negative 5. So based on this, we know that the mean time between failures was 1 over the probability of failure per second. So if I calculate that, what I get is that every 5 hours, on average, we have a failure in our system. Of course, this is for a basic circuit. You can imagine that if you have more complex circuits, this probability of failure and also the mean time between failures can be higher or lower. But by this point, you should have a good idea about how synchronizers can help us to remedy some of the issues that we might have when we have asynchronous inputs in our circuits.